6.13 is evaluating improper integrals. We'll see what that is here in a second. So we are trying to either evaluate improper integrals or determine that they diverge, and we'll see what that means shortly as well. Okay, so we're going to start with this example. We have f of x equals 1 over x squared, so let's look at a graph of that first. Okay, so 1 over x squared is has a value of 1 at 0, and it kind of looks like this bell shape. Like that, okay? Pretend that's symmetric. All right, and then we are looking for the area that is under the curve on the domain. Well, the domain is all real numbers. And so we are looking for the area, however, that's under this curve. However, it goes forever to the left and to the right. So if we were going to try and write that as an integral, we would say that it is the integral from negative infinity to positive infinity of the function 1 over 1 plus x squared. Okay, now we have an issue here because of the infinities. There is one thing we can do to make this a little bit easier. We know that we're finding this entire area under here, and because of the symmetry, we know that that would be 2 times this area. So we can get rid of one of these infinities by calling this twice the integral from 0 to infinity of 1 over 1 plus x squared dx, but we still have an infinity up here. Okay, so back in chapter 1, we talked about like what can we and can't we do with infinities. We can't evaluate with infinity as in a definite integral because if that is our b value, when we plug b into our antiderivative, we might end up with doing some arithmetic that's not possible, like infinity minus infinity or infinity divided by infinity or something like that. So what we're going to do instead is we are going to replace this with a new variable. We're going to pick a variable. T is a really common one. A is an option also. And we're going to replace that, and we are going to stick a limit on the front of this. Okay, so I'm going to write that as the limit as t approaches infinity of the integral from 0 to, now that limit is a t, limit being this word and this word here, of 1 over 1 plus x squared dx. And then this is a definite integral I can evaluate with the limit being the last thing that gets done. Okay, so this is, okay, keeping our limit notation, limit as t approaches infinity of, and then I'm just going to write my antiderivative and group this together, showing that it's before the limit part. So this is a tangent inverse, so tangent inverse x, and we're evaluating from 0 to t. Okay, coming over here, so that still, I have my limit notation. Limit is t approaches infinity. So tangent inverse of t minus tangent inverse of 0, which is just 0. And now we want to know, okay, as t approaches infinity, what does tangent inverse approach? As a reminder, inverse tangent, we're saying tangent of what angle is equal to this value. So tangent of what angle approaches infinity. And because we know what the graph of tangent looks like, because it's this, we can see that it is right. Why is it not writing? We can see that it is pi over 2, where we have an asymptote and where we're approaching infinity. So that is going to be pi over 2 minus 0, which is pi over 2. So that is the area. Oh, I forgot my 2, didn't I? That's the area under half of that. Let's go back and fill in the 2 real quick. I'm going to keep the 2 in front. Okay, 2, 2, 2. So, all right, just kidding. There we go. The area under the whole curve is pi. Okay. All right, so generalized a little bit, if we have infinities as our limits for a definite integral, either from a constant to infinity or from negative infinity to a constant, then we can split this and say the limit, or we can change it and say the limit as t approaches infinity, or whatever a new variable would be, and then stick that on the front, evaluate your integral in terms of t, and then find the limit at the end. Same thing over here we would do as t approaches negative infinity if we had the constant up here. If we have a limit from negative to positive infinity like this first one, here we were able to use symmetry and do twice the integral from a constant to infinity. If we can't do that, then we could just pick any point where we split the integral into two. 0 is a common one, and we could do the integral from negative infinity to 0 plus the integral from 0 to infinity, and then stick a limit on each one of those integrals where something is approaching either the positive or the negative infinity. It's unlikely that that will come up in a way that you don't have symmetry, but it is possible, okay? All right, so if the limit exists, in other words, if there is a finite value for a definite integral, then we say that it converges, okay? If there is no limit, like if the integral approaches infinity once we're evaluating the limit, then we say that it diverges. So diverges means it will go towards positive or negative infinity, or doesn't exist for some reason. Think like sine and cosine that oscillate as we go towards infinity. But if we do have a real solution, we say it converges. Now, we would say what it converges to, like we would give this one, we would say this converges to pi, this previous example. We don't just say, yes, it converges, but we are going to see some things in a later chapter where our primary goal is not necessarily figuring out what they converge to, but just determining yes or no, do they converge, okay? All right, so let's look at some more examples here, and if you want to pause it and try them and then check your work, you're welcome to. Okay, so here I see I'm going from 1 to infinity, so I am going to write this as the limit as t approaches infinity of the integral from 1 to t of, come on pen, 1 over x dx, okay, which is the limit as t approaches infinity of, and so I have an antiderivative there of natural log of absolute value t, natural log of absolute value of x from 1 to t, okay, which is the limit as t approaches infinity of natural log absolute value of t minus natural log of 1, which is 0. And then when I plug infinity in, natural log of infinity does approach infinity, so we would say that this one diverges, okay, because that approaches infinity. Which, if we think about the graph of this one, this one's an interesting one. This is called the harmonic series. This is a term you will need to know for sure later. Okay, this is the harmonic series. 1 over x from 1 to infinity. Okay, well, we know it starts up here. Okay, but it does this. Okay, so this one right here, even though this gets closer and closer and closer to the asymptote at 0, the amount of area that it continues to accumulate under there does not approach 0, like the change in area does not approach 0. So we say that this diverges, okay? Now, this one right here is a little bit different. Let's go ahead and evaluate this. So putting a limit on the front, limit as t approaches infinity of the integral from 1 to t of 1 over x squared, which I'm going to write that as x to the negative second because I'm using power rule. So this is the limit as t approaches infinity of negative x to the negative first, or negative 1 over x from 1 to t, which is the limit at infinity of negative 1 over t minus negative 1 over 1, so plus 1. Okay, then when we evaluate that, this goes to 0. Remember, infinity in the denominator goes to 0, so we end up with 1. So this one converges, okay? 1 over x squared from 1 to infinity looks similar, okay, comes from up here, looks similar, but it is flatter. It jumps down much more quickly to the right of 1. And so this is actually a finite area, okay, of 1, whereas this one, this one is an infinite area, which is an interesting concept. Like I said, we will talk about that quite a bit more when it comes up in a later chapter. So I'm going to stop this for now and do the other types of infinities in the second video.